Hello everybody and welcome to this first video about the kinetics topic from A-level chemistry. In this video we'll be taking a look at how we can measure the rate of a reaction and also at collision theory, which is how we can control the rate that chemical reactions occur. The rate of a chemical reaction is a measure of how fast the reaction is occurring. Some reactions are incredibly fast, for instance explosions, and some are much slower, for instance rusting. In questions, you're likely to be looking at some observable change and measuring with a stopwatch or a timer how long that change takes to occur. And it's important to say from the get-go that if something takes less time, that is a faster rate of reaction because the same change has occurred, but it didn't take so long for it to happen. These changes can take a variety of different forms, but in general what we'll be doing is timing how quickly a reactant is used up or how quickly a product is formed. Typically we'll be looking at a volume of product, for instance a gas, which might be measured in centimetres cubed, or we could be measuring an amount in moles, or we could be measuring a mass change in grams. Those are our three likely ways that we're going to quantify our amount of substance produced or used. And then time will typically be in seconds, but it could be in minutes. And so the rate of the reaction is going to be calculated by dividing this quantity of reactant used or product formed by the time. And so if we are measuring mass, and time is in seconds, our units of rate of reaction is going to be in grams per second. If we were doing volumes, then it would be in centimetres cubed per second, or moles, it might be moles per minute or moles per second. And so the units will always be the quantity on top per second or minute, whatever our units of time are. I'm going to make a longer video about the required practical for kinetics, but to briefly illustrate the concepts here, if we are measuring a mass change, we might start with all of our chemicals on a balance, and we would over time record what that mass is as the reaction proceeds. And that mass is going to decrease because we're going to be producing, in this instance, carbon dioxide gas. And we can quantify this rate by, say, if our mass went down by 2 grams in 2 minutes, that is a decrease of 1 gram per minute. If we wanted it in seconds, we could do 2 grams divided by 120 seconds, and so that's 0.0167 grams per second. And they might ask us a question about the number of decimal points on our balance, particularly if the mass change was very small. We would want a very sensitive piece of equipment that measured to, say, 2, 3, 4 decimal points. And another procedural error could be if there is gas escaping during this experiment, we need to make sure that this gas is a heavy gas, because if it was hydrogen, the mass change is likely to be very, very small indeed. In this instance, a different technique might be necessary. We might need to actually collect that gas that was produced using a gas syringe as shown on the left, or collecting the gas over water as is shown on the right-hand side. Both of these techniques will yield the same type of units, so centimetres cubed per minute or centimetres cubed per second for our measure of the rate, but they do carry an error with them, which is that as you add one chemical to another, that gas starts to get produced, and reactions are always fastest at the beginning, and so the time between the addition and putting our bung and delivery tube in is going to mean that we're going to be losing our gaseous product during this really fast stage of the reaction, and so the volume that we collect is very likely to be smaller than we might typically expect. Chemical reactions are always fastest at the beginning, and that's because the concentrations of the reactants is at its highest at the time when you start the reaction. As time goes on, the reaction will slow down as the concentration of those reactants decreases, and then the reaction will come to a stop once one of those reactions has been used up. And you can tell this has happened from a graph, for instance, because you've got this plateau at the end showing that no more reaction is occurring because one of those reactants has been used up. And you can also see that the reaction is fastest at the beginning because that's where the gradient is the steepest, as you can see. You can actually quantify the rate of reaction at any particular point from a graph by drawing a tangent to the curve at any time that you choose, for instance, time 0, so the start of the reaction. This is called the initial rate of reaction. So you draw a tangent, and that tangent follows the line of the curve at first, but when the curve starts to curve, the tangent continues in a straight line. Tangents are always linear. And so you could measure the time later on in the reaction, here for instance. And so what we'd need to do is we'd need to make sure that our line matches the gradient of this graph at this point, but obviously the graph was steeper just before this point and it's getting more gentle after this point. So our tangent needs to capture the gradient at a particular point. And then we calculate the gradient by doing the change in y divided by the change in x. And because the units on the y-axis are cubic centimetres and the units on the x-axis are seconds, the units for our tangent will be in centimetres cubed per second, just like the units of rate of reaction that we've already looked at. Another way of measuring the rate of a reaction is if this reaction produces a precipitate. Now, precipitate is a solid that forms during a reaction involving solutions, and a great example of this is the disappearing cross experiment. And that's where hydrochloric acid reacts with sodium thiosulfate, and we get a cloudy white precipitate forming of sulfur, bordering on yellow. Now, what we're doing here is we're measuring the turbidity of the solution, in other words, the cloudiness. And once the turbidity is such that we can no longer see the cross when we look down through the conical flask or look through a boiling tube, then we stop our timer. So this is a really simple experiment, but it's not always suitable and it's not always particularly sensitive because we're making an assumption that the amount of precipitate formed each time the cross gets obscured is the same. And that's our only way of measuring the amount of precipitate that's being formed. And so we're assuming that it's a constant each time. And so the rate of reaction can be quantified by doing 1 divided by time, because the precipitate is a constant, so we can substitute its amount from the top of the expression with any number actually. So 1 over time is typical, but could be 100, could be 1000, anything really. And so this is a problem because if we change our glassware during our experiments, we've got a different depth of solution, and this could lead to a different rate of reaction due to some external factor, not, say, concentration or temperature, that we might be investigating. You need to be able to suggest a method for measuring the rate of a reaction just from simply some details about the experiment itself. So for instance, you need to be adept at looking at the chemical equation and paying attention to the state symbols. If we can see that a gas is being produced, that means that either of those first two methods is appropriate. So measuring the mass change in this chemical reaction, particularly if we've got carbon dioxide, which is quite a heavy gas, or collecting that gas, measuring its volume at regular intervals. Alternatively, we're looking for the existence of a solid in the product, so that would be a precipitate that would form during this reaction, so we'd be looking at the rate of formation of that precipitate. All of this depends on our use of the state symbols. Collision theory states that before two particles are going to react together, they need to collide. Not only that, they need to collide with enough energy to trigger a reaction. And so therefore the rate of a chemical reaction will depend on the frequency of collisions, so in other words how often the particles are colliding, and the energy transferred during that collision, so in other words how forcefully do these particles collide. And so that means that anything that affects the frequency of collisions or the energy of the collisions is going to affect the rate of a reaction. A great phrase to use when describing collision theory is to look at the factors that affect the rate of a reaction and explain that the changes that we've caused have all increased the frequency of successful collisions, because that captures both the frequency of collisions and also the likelihood of these collisions being successful by, say, having more energy during the collision. So increase the frequency of successful collisions. And we're going to take a look at the things that affect the rate of a reaction now. In a chemical reaction that involves solids, the rate of the reaction will depend on the size of these solid pieces. So for instance, if you consider a reaction between metal and acid, if we have a single piece of metal with a low surface area, that will react more slowly than a series of smaller pieces with collectively a higher surface area between them. And that's because the collisions between the acid particles and the metal particles are going to be more frequent, and therefore there will be a faster rate of reaction. We can quantify this effect by working out something called the surface area to volume ratio. If we take a large piece of metal with each of its dimensions being 2 centimetres, then the volume, which will be 2 cubed, is going to be 8 centimetres cubed. And then the surface area will be 2 times 2 for one face, multiplied by 6 for the 6 faces, so 24 square centimetres. And then the surface area to volume ratio is calculated by taking the surface area, dividing it by the volume, and we get 3 as our answer. If we then looked at a smaller piece of metal with a dimension of 1 centimetre, then the volume of this cube will be 1 cubic centimetre, and the surface area is going to be 6 square centimetres. And so the surface area to volume ratio is 6 divided by 1, which gives us 6. And so this is a much higher surface area to volume ratio. We have in fact doubled that value by halving the dimension. And that's a factor that you need to be able to work with. For every increase in dimension, you will have the same decrease in surface area to volume ratio. If the dimension is 10 times bigger, the surface area to volume ratio will be 10 times smaller, etc. Another way of looking at this is, in order to have the same volume of small cubes that we have in one large cube, we would need 8 of these individual cubes, because 8 times by 1 gives us our 8 cubic centimetres. And that would give us a surface area combined of 48 square centimetres. And so that is a much bigger surface area for 8 small pieces compared to 1 large piece. We've got twice the surface area. And so therefore we will have twice the frequency of successful collisions. Concentration is a measure of the number of particles per unit volume. And there can be a variety of different units for this, depending on how we're measuring our number of particles, whether that's moles or mass, and what our unit volume is. Typically cubic decimeters, but it could be cubic centimeters or something else. And how concentration affects the rate of reaction is quite simple. If we take a look at something that has got a low concentration of one particular particle and compare it to something which has got higher concentrations, we can see qualitatively that a higher concentration shows more particles per unit volume, and so therefore there will be more frequent successful collisions and therefore a faster rate of reaction. And in fact, this is exactly the same pattern if we look at pressure. Whereas instead of looking at the number of particles per unit volume of solution, which is what concentration is, pressure is just simply the number of gas particles per unit volume of space. And once again, for the exact same reasons, a higher pressure means that there will be more particles per unit volume, so the collision frequency will be increasing, and that means we will have more frequent successful collisions and therefore a faster rate of reaction. Increasing the temperature will also increase the rate of a reaction. And to illustrate that, we need to consider 2 situations. One where the particles are reacting with a lower temperature, and another where the temperature is higher. And the higher temperature will have a faster rate of reaction. The reason for this is twofold. First of all, there is more kinetic energy when the temperature is higher, and therefore the particles will be moving faster. As a result of that, they will be colliding more frequently because they're moving faster. Not only that, each collision will occur with a greater amount of energy, so each individual collision is more likely to be successful. Overall, these 2 separate factors contribute to a significantly increased frequency of successful collisions and therefore a faster rate of reaction. We can understand chemical reactions a bit more deeply if we consider a concept called the activation energy. This is the minimum amount of energy that particles must have in order to start a reaction. And so if we first of all consider a situation where we've got 10 particles and they've got each a different amount of energy, and let's say the activation energy is 12. you can see that in this situation that we've got here, a very small number of particles have got energy equal to or greater than this activation energy. I've got 3 with this activation energy. If we raise the temperature, what we end up doing is we end up increasing the energy that the particles have got. And so now you can see that a greater proportion of these particles now have 12 kilojoules per mole's worth of energy or greater, and so therefore a greater number of these molecules is now going to be able to react successfully when a collision occurs. And so this will lead to a greater frequency of successful collisions because more particles have got the required activation energy needed for the reaction to occur. There are 2 things that we need to know about catalysts: what they are and how they work. First of all, catalysts are defined as being something that speeds up the rate of a chemical reaction and is not changed by the process, or it's not used up by the process. Catalysts work by providing a different pathway or an alternative route for the reaction to occur, and this pathway has got a lower activation energy. A nice metaphor for this is if we imagine a person on one side of a hill and they need to walk over the other side of the hill. In order to do that, they need to put in some energy to get to the top of the hill before they can get to the other side. A catalyst in this metaphor is symbolised by a tunnel, and that tunnel is not quite as high up as the top of the peak, and therefore that allows this person to get over to the other side of the hill without putting in the energy it required to get over the top of the hill. And different catalysts will have different efficacies because they are a tunnel at different heights up the hill. They reduce that activation energy by different amounts. If we just illustrate this in a similar way to before, looking at the activation energy that these particles have got, you can see that we've got a situation where 3 particles have got the necessary activation energy of 12, and that means that they can react successfully and the others don't have enough. If we consider a catalyst that is going to reduce this activation energy down to 6, for instance, that means that we've got 5 additional particles with energy equal to or greater than this value that can now react that couldn't react before. And so you can see that we will have a greater frequency of successful collisions because a greater number of particles have energy equal to or greater than this activation energy. We can illustrate catalytic activity by using something called energy profiles. If you take a look here, I've got 2 energy profiles. The one on the left is for an exothermic reaction and the one on the right is for an endothermic reaction. And you can tell this because the products have got less energy than the reactants on the left, and it's the other way around on the right hand side. You can see that I've labelled the activation energy here, and that is the distance between the starting energy of the reactants and the peak of this reaction profile. And there's a different activation energy on both sides. Typically, endothermic reactions have a higher activation energy. If we add a catalyst to this, what we do is we redraw this reaction profile kind of hill shape, and the peak of this hill is lower than previously, again symbolising the fact that the activation energy has been reduced significantly, and so therefore a lower energy collision will now result in a successful reaction. And so the presence of a catalyst will definitely speed up the rate of a reaction. And the quality of the catalyst will be shown in the reaction profile by the amount that this activation energy has been reduced. A better catalyst will reduce the activation energy by a greater amount and lead to a greater increase in the rate of reaction. You can do an investigation into the quality of a particular substance as a catalyst. For instance, you can look at the decomposition of hydrogen peroxide, which decomposes into oxygen and water. Oxygen is a gas, and so we can collect this gas and measure the rate at which this gas is produced. And so on this occasion, the rate of reaction is going to be in centimetres cubed per second because it's a volume of gaseous product produced over time. Now, this reaction will happen anyway at room temperature, but really, really slowly. And so what you can do is you can add a catalyst to this conical flask where the hydrogen peroxide is, and you can see how much of an effect this will have on the rate of production of gas. Some catalysts will have a really significant effect, for instance manganese dioxide, others will be far less effective. You might also investigate this in biology as well by looking at the enzyme catalase, because this enzyme is acting as a catalyst and it is going to be present in things like liver and potatoes, and you can look at the effect that these different substances have on the decomposition of hydrogen peroxide and use that as a measure of the concentration of catalase enzyme present in different substances. When you do this, you should always use a control, and so you should test this with no catalyst at all or with something completely inert, just to see whether adding a solid to your hydrogen peroxide will affect the rate of production of oxygen gas, even though we know that this solid, say for instance ceramic beads for instance, is not going to be a catalyst at all. But this will allow us to state conclusively that the solid that we've added is the reason for this increased rate of reaction. Okay, that's the end of this video. I hope it was useful. Don't forget to check out my Maxwell Boltzmann Curves video on the same topic. I'll see you again soon.